Yes. So. Yes. Thank you, Roxana, for the introduction. I'm Filippo Mantovani from the Barcelona Supercomputing Center. I will talk a little bit about the Mont-Blanc project and the experience that we had importing applications to ARM-based clusters. So, of course, I have the usual introduction about the project for those in the room that don't know about Mont-Blanc. The idea is to leverage the fast-growing market of mobile technology for scientific computation in high-performance computing in data centers. So this is our timeline. We started long time ago in 2011 with the first phase of Mont-Blanc. Then we got Mont-Blanc 2 and Mont-Blanc 3. But all these phases are where they do have a structure in common. So basically, we always had a big part in deploying hardware, deploying prototypes, and hand-in-hand part in software, enabling the ecosystem that you need in order to run on a cluster based on ARM technology. And from this experience of deploying hardware and software, you always learn something. So we always have a look ahead work package in next generation studies. And this was true in Mont-Blanc 1, where everything was based on mobile technology. I mean, John this morning was mentioning the Raspberry Pi experience of Red Hat in 2012, 2011. So very similar idea here. And Mont-Blanc 2, we start looking at server technologies because ARMv8 in the meantime become available. And we did an effort in the system software and looking next generation, the pre-exascale compute node. We start thinking about it. And Mont-Blanc 3, that is now the reality, is 100% focused on server technology. There is no mobile basically anymore there. And the software is basically focusing on application now, on mini apps or really industrial application. And the next generation studies are more like, let's try to have a product out of it. And this is actually the product that I'm going to mention, the Mont-Blanc 3 demonstrator that I'm going to show you later. So this is the transition over time. So from mobile, the crazy guys trying to do HPC on whatever, small devices, the transition till the idea of installing big system in data center is becoming a reality, right? Fortunately, my introduction about the project can stop here today because tomorrow we will have Etienne, the current coordinator of the Mont-Blanc 3 phase, presenting the rest of the details of the project in another workshop. So I invite all of you, if you want more details about the project, to go to the talk of Etienne tomorrow at 9:50. So about the Mont-Blanc contributions, as I said, deploying ARM-based prototypes, put there some system software in order to be able to use them as a cluster, as parallel machines, and then try real scientific codes. This has been always our focus. And from this experience, learn from next generation studies, next generation cluster, next generation architectures. And of course, as several partners of the project are involved in academia and education, we have the educational challenge that I started 3 years ago now of the student cluster competition. I will annoy you with one slide at the end about this. So today I'm going to focus on the left part of this slide. I have 2 slides about our platform. As I said, we started with the praise prototypes that were Android development kits stacked one on top of the other, and then the mini cluster, a very similar idea, and then the Mont-Blanc prototype that was the real deployment of the first phase of the project, and then the 64-bit mini cluster ARMv8 that are still up and running, and the Mont-Blanc 3 demonstrator that I'm going to show you in a couple of slides. So today I'm going to talk about these 2 objects because are probably the only 2 that you cannot find in a store, actually, or, well, at least the Mont-Blanc 1, maybe the Mont-Blanc 3, you can find it. You can buy it soon. So the Mont-Blanc 1 prototype, okay, this is the credit card form factor node card where you have one instance of Linux running. And basically, You have a dual core Exynos 5 SoC with 2 core plus a Mali GPU that is OpenCL programmable, 4 GB of low power DDR3 RAM, and some local storage and some network, bridging USB 3 to Ethernet. So this is the setup, and we put several of them, thousands of them all together, installed in cluster, and this is operational since more than 2 years now, still operational, so if you want to run. So this is what I mentioned before with the purely mobile experience. This is the SoC that was in one of the tablet, Nexus, whatever, I don't remember. So the envelope is HPC, but the SoC is really mobile. So this is the other reality that we are living now. We are living in high-end server technology. So this is the Dibona Mont-Blanc 3 demonstrator that is going to be a reality soon in the Mont-Blanc 3 phase, in the Mont-Blanc 3 project. And you see that is based on the Cavium ThunderX 2 CPUs and installed within the Sequana infrastructure that is the Bull Atos high-end infrastructure. So as I said, Etienne is here. He is from Bull, so he has details about this. These are the 2 platforms that I wanted to present, but we have several others that we call, as I said before, mini clusters. So we have hardware. What do we need? We need system software to operate it. So I have to admit I'm guilty of this. We started hacking a lot, so we were not John compliant at the beginning, actually. But there was no OpenSPC, there was basically nothing. So, but still, now we have something that is in place. We have this Mont-Blanc, what we call Mont-Blanc system software, and it is pretty much standard, and it's tested on all our platform, and it's mostly based on open source packages, and there is this willing of this idea of contributing to the community and not just hacking. Even if the attitude in my presentation will reappear. Okay, so, and one point is here that we did a small effort, or well, a relatively big effort in standardize the power measurement. Actually, my talk here last year was complaining about the non-standard way of measuring power in ARM. So I don't go that road because I already did it last year. But so we have hardware, we have just this high-end view of software. What can we do now? Just run applications. So when I say applications, I mean benchmarks, I mean mini apps, but I also mean production industrial codes. And especially Mont-Blanc 3, we have one company that is involved as a partner in the consortium that is providing codes, real use cases to the project. What do we do with this application? We usually trace this application with different objectives. So the first objective is to test the current solutions. When I say current solution, I mean hardware solution and software solution. So I will have a couple of slides later of the test that we did on the Cavium ThunderX, and also about the software solution, the test that we did evaluating the ARM HPC compiler. And with these traces, we can also understand the code limitations. And then we have an effort within the project that is, say, helping the developer restructuring their code using modern runtime solutions like the one proposed in OMPSS OpenMP4, basically. So that is going in the direction of taskifying the code, and also testing new techniques like the dynamic load balancing. I have one slide mentioning this. What I'm not explaining in this presentation, but is still part of the project, is that with the same traces or very similar traces, we can say, we have a simulation infrastructure in which we can replay these traces, just changing architectural parameter, and see, say, how this impact next generation machine. This is called multi-scale simulation architecture, MUSA. So Michael Moreto from BSc is here, so if you want more details about this last point, I can point you to him. Okay, good. So as I said, I want to show you a couple of examples of this, what we do with these applications. The first step was enabling the PAPI support in the Cavium ThunderX. We did, at the time in which we started was the performance monitoring unit was not supported by the kernel. That time was, it was 1 year ago, I think, a little bit more. It was kernel 4.2.6, so we passed the kernel in order to support, to be able to access the performance monitoring unit. And then we extended, this part of the kernel is now not needed anymore because this is already in the kernel. So if you buy Cavium ThunderX today, you install a Linux with the kernel higher than 4.4 and you will get access to the PMU. What is still not in the as far as I know, in the main branches of PAPI and libpfm, the possibility of accessing the hardware counters in the CPU. So we extended that in collaboration with Cavium. And what we get is a patch that we started hacking here, but we did it I hope in the right way, because we released this patch to both mailing lists of libpfm and PAPI, and we are working, or we are in collaboration with PAPI and libpfm, open to integrate our changes in order to have access to the hardware counter in the Cavium ThunderX. Why this is important? Well, because this enables the advanced analysis that I'm going to show you now. As example, I took a code that is simple to understand and say nice to show because it has nice faces. That is the lattice-Boltzmann code structured with MPI plus OpenMP parallelizations. It's basically mixing so it's studying the mixing layer of fluids at different densities. This is just for you to know. And this is structured with some serial part at the beginning, initialization here. Well, this is not working. Okay, the initialization part on the left. And then you have phases. I mean, here we have 10 iterations, and then you have green phases and blue phases that we call propagate and collide. Propagate is memory bound, and collide is compute bound. The color code here is representing the IPC, the instruction per clock cycle. So basically, you see that the memory bound part has a low IPC, and the collide part that is compute bound has a high IPC. Okay? So on the x-axis, you have the time. On the y-axis, you have the thread, and the color is basically giving you the quantity. Okay, so this is just to put you in context. So in order to get these trace, you need the hardware counters, because the instruction per clock cycle, you need to read this from the CPU, right? So you see that even for a plot like this, in which you already have a good understanding of the structure of your application, okay, it's simple, but still, you need access to the hardware counter. But with the hardware counters, we can not only do this kind of plots, but we can do a little bit more advanced analysis. And here we have a plot in which we use clustering techniques in order to study how the section of the code are evolving running with different number of threads. And here you see, with the same color coded before, in blue you see the part that is compute bound, and in green you see the part that is memory bound. And the plot is IPC on the x-axis and total instruction on the y-axis. And here basically you clearly see what we already, I spoiled here this plot, because the compute bound part is scaling perfectly. So you have the blue part that is going from 6 to 48 cores and is basically not lowering the IPC, while the memory bound has the opposite behavior, right? So every time that you add threads, you add people competing for one resource, it is the memory, so you have lower and lower IPC. So these are the kind of studies that we did and we do every day, and that we can do if we have access to this kind of performance counters. As I mentioned before, we put our attention on the power measuring, so the possibility of measuring power on our platforms. And actually, it's a little bit a nightmare on our platform, because we have several different mini clusters with server technology, embedded technology, with onboard meters, off-board meters. So the sampling rate is different on every system, and we have synchronization issues. But still, we try to integrate the power measuring possibility that we have in Slurm. So whenever you do an S-info on your cluster, on your login node, you see that you have a queue in which you can schedule jobs. And if you schedule a job in that queue, your job will be running, and at the end, you will find a CSV file with the power information in it. And actually, the same file is, you can visualize it with Paraver. And here I show you the same trace as before, or very similar, in which we run the same code as before. You can see the green and the blue part. Same metric as before, the IPC. And this is in the high part. Sorry, my pointer is not working, so I will use the mouse. So here you have the IPC, but at the same time, you can see the power consumption. And you can see here, you can see the limitation of this platform. Here we are on the ThunderX machine, in which we use an external power meter that are very low frequency sampling. So we have a time shift, and we have coarse power measurements. Of course, we cannot detect the iteration, right? But we will see that, well, actually, in this plot, we are using another device in which we have high frequency sampling rate for the power. Okay, and here, yes, we have gigaflop in the higher part here, and then we have the power. And here, yes, we can measure more several measurements per second, in the order of 100 per second. So we can detect the phase of this application. And then we can merge with these two and just get them the gigaflop per watt, the metric that is obsessing everybody, right? And we can have it and explore it at the granularity. I mean, we can zoom in. Right now, this is an image, but in the tool, in Paraver, you can zoom in and understand which part of your code is running at which efficiency. And I think this is really important. And this is possible because we try to get the power out of our mini cluster, and because we got the support with the hardware counters with PAPI, with a standard library like PAPI. Okay, good. So this was a little bit the story of one of the test case. In reality, you can do also, I just mentioned this because we were debugging these mini clusters, and here I'm not plotting IPC, here I'm plotting the frequency. Okay, if you see the range here is going to 1.2 gigahertz to 1.7 gigahertz. And you can see that there are spots in this application that happen to be the same as before, but in which the frequency is lower, is going down. Basically, it's always running at maximum frequency, but at some point, something happened. It's still not understood. So these tools, the message here is that these tools are not only good to debug or to understand, analyze your codes, but they are also good for deployment whenever you touch your hardware in order to understand what's going on. So if you have a problem with a governor, these kind of things. And also, the other good point is that you are one click away to have the energy to solution of your application. So not only the efficiency, but also you can get really easy with one click the energy to solution of your application, also in a portion of your code. So think about different implementation of the same application, which is using more or less power, why, and so on. So you can try to investigate it with this kind of tool, and we have examples in the project. Okay, so as I said, we do not only test hardware platform, we also test software solutions. And here, well, this was more slides, but I had to remove it because actually we did this study in July, and in the middle of August, we got a new version of the ARM compiler, so I didn't want to show you all the data. We will rerun our analysis now after summer. So the idea was to do a comparison between GCC 7.10 and the ARM HPC compiler 1.3. So The methodology was to take a polybench, so a benchmark, and then mini apps, Lulesh and Comdi, and then a real application like Quantum Expresso that is using linear algebra and also FFTs in order also to include the analysis of the R performance library. This was the idea. Actually, this is still the idea, and we are going to show all the tests the preliminary tests that we did in a poster in supercomputing. But still, the message here is that what we notice is that the R performance library is generating a lot more instruction. I mean, here you see the total instruction, the total execution, the total instruction. On top, you have the ARM HPC compiler, and bottom, you have the ZCC. But on the other hand, on the left side, you have the histogram of the IPC, so of the instruction per clock cycle. So basically, you have a lot more instruction with the ARM HPC compiler, but somehow they are processed faster. So this is balancing not very good in the sense that the time you see that it differs. But still, this is very interesting from our point of view. This is one of the findings that we got and is still under development. But what I'm showing here is that we evaluate this kind of software solutions, and we try to use the same tools that I showed you before in order to get insight. And we are collaborating with ARM. I'm in contact with Chris Gauthier about this, and he's commenting these results every day and providing feedback. So this is a real collaboration. Good. So I mentioned the test of the platform, software and hardware, and now I want to show just one slide about the optimization, or say the improvement that we can have with the programming model. So here, for this example, I consider another code that is Alia, is a code developed within BSC. It's a finite element codes. If I show you yet another trace with different colors, but anyhow, here in this part, this application has atomic operations. So it's coded like OMP parallel force plus atomics. And here we have two suggestions. Say we implemented two solutions. One is just a technique of coloring, so remove the atomics and just use the parallel 4. And the other one is using commutative multidependencies. That is a fancy name for saying, let's try to update, let's try to tell to the runtime that he can update one side or another, but not the two at the same time. So instead of linearizing with atomics, you just say, you can do this, you can do this, you can choose the commutativity, I mean, you can choose the order, but don't do it at the same time. So, and here, this is part of OMPs right now, but we will push it in the OMP standards, or we suggest it to the OMP standards. And here I have a little bit the results, even combining this with dynamic load balancing. When I say dynamic load balancing, it's a simple concept. Basically, whenever you have a process that arrives first and is going idle, can lend his resources to another process within the same node. This is the idea. Okay, and here basically the takeaway message is that with all these techniques on this code of finite element code, we get, so summing the commutative multidependencies plus the dynamic load balancing techniques, we can go even better than the MPI only implementation. And so basically here the MPI only is the green part, and if you look at the dotted lines, this is the OMPs plus DLB implementation. Okay, so this is one example of the kind of changes that we try to implement in the runtime that are more or less transparent for the users and that can benefit, and the user can benefit of them. Another example, but this is, I pass it a little bit faster, I mean, it's just the same code. When you have coupled code, you have the fluid part and the particle part, and you have these two processes in the same code. Well, this DLB technique can benefit, can produce benefits to the time, to the overall time to solution. And here, basically, you have one of these example with DLB land when idle. That is exactly what I was mentioning. And you can see that basically the overall execution time with this optimization is decreasing in a space in which we test different combination of process and threads. Good. So this is, if you want, I show you, now I do a zoom out. So I show you a little bit of spots of very specific example, and now I zoom out and I show you all the Mont-Blanc 3 application. That is a little bit of a nightmare. I just put it here just for you to understand that we are not just hacking here and there, but there is an overall picture and there is an overall strategy with all these codes. And actually you can see here that the partners, University of Graz, HLRS, BSc, and we have AVL, that is a company in Austria that is providing use cases. Okay, yes?
Before you leave that chart, so it's all good stuff. One of the things in Mont-Blanc 3 that we talked about needing to do more of is vectorization.
Yeah.
Where is that fitting in your code improvement section and specification and algorithms, but should we have a vectorization component there as well? Or is that already incorporated into some of those?
Okay, so far, as far as I understood the strategy within Mont-Blanc 3, the vectorization part was more part of the architectural study part.
Yeah, but doing it without modifying the applications then causes problems, because if you applications don't vectorize, then
they do.
applications that don't vectorize on vector hardware.
I totally, yes, I understand.
Sorry, just a suggestion, man.
Okay, so noted. Thank you. Yes, and so take note about the vectorization here. And yeah, no, I arrived at my conclusions, and so also a little bit try to explain the title. So the hardware actually is not worrying too much. The hardware will evolve at some point eventually, so it's not a problem. Also because you have other market pushing the hardware. You have the mobile market, the automotive market, so I'm not worried about the hardware part. Tools can help understand the real problem and suggest evaluate alternatives. And here I think I convinced you that having access to the performance counter in the Cavium, as a very small example, had benefits in several cases and in the performance analysis. And also correlating performance and power, so having access to the power information, even in the RAPL way, would be very, very useful. And the programming model and runtime will help overcome some of the limitations. Still, we have a lot to do, especially in vectorization. And anyhow, the key message here is that the work performed here is not 100% ARM-based. And actually, here is the explanation of the butterfly effect. I mean, what we are doing here is mostly helping the community. And actually, most of the thing that I was showing here is not ARM-specific. So something that is really going beyond and helping evolving the high-performance computing in general. So who knows which are the effects of what we are presenting here. As I said, I cannot finish without this slide. I'm sorry. This is the educational challenge that I mentioned at the beginning. Since 2015, we participated in the student cluster competition, always with an ARM-based cluster. And well, the first year we struggled, and the following years we were able to submit all the results of all the challenges, and I'm pretty happy of it. I mean, we were not awarded of any performance figure, of course, but still, I think this is a very nice experience. First of all, for the students, for me, and also for ARM and the ARM in HPC as well. And yeah, we had the last 2 years, we got this Fan Favorite Award, and this year I'm still looking for a cluster. So if somebody in the room has platform, please contact me. I know that there are a lot of nice hardware out there, so please That's basically it. I want to leave you with the information of the consortium and my contact in case you want to complain about vectorization and more and more. Thank you very much. Okay, thank you very much. That's it.
Thanks, Peter. Any questions in the audience? You can ask more about vectorization. Okay, or if not, to stick on time, I welcome the next speaker, Sumoto Shinji from Fujitsu, who will be talking about the ARM HPC ecosystem.